Okay, so we've talked about different types of science and, not necessarily different types, but basically what good science is. But we haven't talked about how to collect science in a proper and accurate way. And so we need to discuss accuracy and precision. So not only do you need to make sure that when you read and interpret science, it's coming from unbiased sources, one of the ways that science is becomes unbiased and is done in the proper way is to take into account the accuracy and precision of the data collected. So if you're going to properly interpret data that you collect from a laboratory, it's really not possible to do that without taking into account the accuracy and precision of your measurements, or for you as a scientist deeming whether another scientist did good work, you need to look at whether their methods were appropriate, whether they had the appropriate accuracy and precision. So that's what we're going to talk about next. Okay, so what is the difference? So let's say you get on a scale and it's always reading that you're 5.42 pounds too light, although some of you may like that, well, some of the guys might be trying to gain weight, but you get used to it. You're like, sweet, I'm only a certain weight. But the thing is if it always reads 5.42 pounds too light, it's very precise because it's making the same error in the same type of way, but it is not accurate. So accuracy has to do with how close the measurement is to the real value. Like if you actually weighed 100 pounds, but it was always measuring you at 94.6 pounds, approximately, always 94.6 pounds, it's very precise because it's always coming in too low, 5.42 pounds too low, but it's not accurate because you actually weigh 100 pounds and it's always weighing you less. So precision has to do with how close the measurements are to one another, but not necessarily close to the real value. So obviously measurements that are very accurate and precise are the ones that are desirable. So let's take this. This is a very common way to explain the difference between accuracy and precision. This one here, all of the measurements are coming very close together, but not close to the target. So think about which one this would be. Is this accurate, precise, or both? And this, you should come into, well, all of the measurements, so to speak, or all of the dots are very close to each other, but not close to the target. And so therefore, these are precise, but not accurate. These over here, they're all not close to the target, and they're also not all that close to each other. So this one would be an example of the least desirable, where it's not accurate and it's not precise. This one, all of the dots are close to the target, but not really all that close to each other. This one, the person throwing the darts has a lot of precision, but they're off, right? They're always throwing a little bit too low and a little bit to the right, or I'm sorry, to the left. And so this would be an example of, the dart thrower is very precise, but not accurate. This one, they're pretty accurate. They're always coming really close to the bullseye, but all of their throws are a little bit off from each other, so they're not as precise, let's say, as the person throwing the values in C. Obviously, D is the best. Someone that's throwing darts and they're always hitting the bullseye. All their throws are very close to each other. So this is an example of precise and accurate. Okay, so if you're off, how much are you off by? And that's where we'll deal with percent error. So percent error has to do with the experimental value, and you subtract that. This is the value you got from the value you were supposed to get. So if you were, let's say, measuring the density of water, the density of water is 1 gram per milliliter. That's the accepted value. Everybody accepts that the density of water is 1. 1 milliliter of water weighs 1 gram. But the experimental, let's say you measured it, you measured the volume that you had, you measured the weight, and you're a little off. Whatever you measure is the experimental. So you take your value, you subtract the accepted value. So let's say you got 0.95 here. And then here you have 1, that's the accepted value. Then what you'd have is 0.95 minus 1, and then the accepted over 1. So you'd have negative 0.05 over 1. And then you would end up getting a negative value. So after you multiplied by 100%, you'd end up getting negative 5%, and that would be your error. Okay, so if you have a negative value, that means your accepted value is greater. And if you looked at your accepted value, it was 1, so it was greater. That means, you were off, you came in negative 5% under what you were supposed to. If the error is positive, that means the accepted value is less, which means you overshot. You had if this value here was like 1.05 or something like that, that means that you came in higher than what you were supposed to. And so that's a positive error. Okay, so it's the experimental minus the accepted over the accepted times 100%. All right, significant figures. This is something that can be pretty confusing to people. We're going to go over this much more than just what this video lecture is showing you. So it is a concept we are going to use the whole year. If you don't understand it, a lot of people make the mistake thinking, well, I just got to get through this, take the loss or take the L on this, and then it'll go away. But you are going to be using significant figures in your calculations for this entire year. And if you take physics, it'll be there. If you take an upper level science class that involves computations, it'll be there too. Bottom line is significant figures from here on out in science are never going away. So this may be your first exposure, but certainly not your last. So significant figures show the precision of a measurement. All the digits that you record in your measurement are the digits with certainty plus one extra that's an estimate. And I'll show you what I mean. So the estimate is significant as well. So these numbers are all important or significant, but not all of them are super certain. So let me give you an example. So let's say you had this substance here. I don't know, let's say it's a block or a piece of paper or something. Okay, so let's say we have this substance right here, and we're going to measure the length of it. So we stick it up to a ruler. Okay, so all of these tick marks are significant. So we'd say that maybe this is, we know for certainty that it's at least 11 centimeters. And because of this tick mark, we know it's at least 11.6. But it's not exactly 11.6. It's coming in somewhere in between. And that is significant. That's an estimate, but it's significant that it's in between the 6 and the 7/10 of a centimeter. It's like right here. So let's say it's 11.64. Okay, all 4 of these values were measured. These 3 are certain, and this one here is an estimate. But that estimate is something significant. It does tell you, roughly that it came in between the 6 and the 7, 11.6 and 11.7. And so this value would have 4 significant figures, 3 of which were certain, and 1 that is an estimate. Okay, now if you were to say it's 11.64237, people would be like, well, where in the world is it appropriate to give that level of precision? To say, oh, I've got 11.64237, people would be like, on what basis are these values there? They're not. The issue is sometimes you take a measurement and you compute it with a different measurement, and your calculator spews out all sorts of extra numbers like that, and they are not significant numbers. Your calculator may spew out, kind of like barf out onto the screen, all sorts of extra numbers because it doesn't know what your measurement was about or that it even is a measurement. And it's up to you to kind of truncate that off or round it, I guess I should say, and this is going to be rounded down to the appropriate level, and that would be this. Now, that's not an issue for this. We're just taking a straight measurement. But my point is we wouldn't have just added these on. It's not an issue. You, common sense-wise, probably would have said that the value was something around 11.64. The issue is if your calculator, in a calculation gives you some extra values, you need to know how many should be there and how many should not. And those are the significant figures. So this would have 4 significant figures in the measurement. Okay, so if you're looking at a number, you need to determine when that number is being reported, how many significant figures it has. And we are going to practice this in class. So don't worry if I'm kind of throwing some of this at you fast, okay? So the context for significant figures was on this page. It's when you're in science and you have numbers, usually they're measured. And those numbers that are measured are significant. If they were measured with certainty and one with an estimate, they're significant. If you're looking at numbers that have already been measured, you need to determine the number of significant figures in the measurement. So all non-zeros in a measurement count. Zeros that are in between zeros do count. So for instance, if I had this number, if I measured in the hundreds place and I measured in the ones place, I must have also measured in the tens place. So numbers between zeros count. Numbers in front of a non-zero don't count. So let's say I have this. These are placeholders. They're numbers in front of a non-zero, so they don't count. And then zeros at the end of a number, but they also are to the right of a decimal. Okay, so what I'm saying there, the example there is zeros at the end of a number and to the right of a decimal. So let's say I have this number. These zeros are to the right of a decimal, they count. And if these count, therefore this one does. So if you said, you know, how you, or what would you in that rate? And you said 10.00 seconds. Well, if someone said 10 seconds, you'd probably think in your mind, oh, about 10 seconds. But if someone said 10.00 seconds, that's like, wow, that was like almost exactly 10 seconds. It shows and represents a level of precision. These numbers must have been measured if the person says their time was 10.00 seconds. And so those zeros are significant. Now, if I said, what was your time? And someone said, oh, about 10 seconds. You'd be like, all right, well, was it 11 seconds or was it 9 seconds? Like, I know, my friend, they probably exaggerate. They probably ran like 11 seconds, but they're kind of rounding down to make themselves sound faster. So this would be an estimate, and that zero there would not be significant. So zeros at the end of a whole number are placeholders and do not count unless there's a decimal point used. So then if someone put this here, whoops, put this dot here, this decimal, that's implying that the zero was measured. And so that's how you could signify that you measured the zero and it's not just a placeholder. If the decimal's not there, it's just this has one significant figure. This one has two significant figures. This one up here has four significant figures because there's no reason to put these zeros here unless you measure them. You can write the number 10 without the zeros. Okay, so this is kind of a crash course in significant figure rules. Now we're going to practice and apply these rules. So how many significant figures does each of these values have? Well, remember in this first one, all non-zeros are significant, and then numbers, zeros in between are significant. So this would have four significant figures. This next one, it has two non-zeros, and these are placeholders. Two significant figures. This one, not two non-zero numbers. And then these here, numbers to the left of a number with decimals, these are just placeholders. This also has two. This one, 3. This one, all zeros in between non-zeros are significant, so that means every digit, all 5 of these plus these 2 are significant, so we have 7. And then in this one, if you have decimals, these zeros are here just to be placeholders. The reason this one is here, you could write 0.00456 without this 0. This 0 is here because it was measured. That's why it's written. Therefore, this has 4 significant figures. We're going to practice this more in class. This is just an example. If you got these right, if you don't quite understand where these numbers came from, maybe watch these, rewind and watch this a little bit again so you can hear my explanation. But again, we're going to practice this more in class. Adding and subtracting significant figures. This is something that I'm just going to go over in class a little bit and explain, but we're going to do a lot of practice with adding and subtracting, and we're going to do a lot of practice with multiplication and division. I'm just going to introduce the rules in one example real quickly, but this is going to need a lot more practice. So with adding and subtracting, when you crunch two numbers, you have to look at the level of precision, and basically the answer can't be any more precise than your least precise measurement. So overall, the overall number of significant figures in your answer doesn't matter. What does matter is that your answer can't appear to be more accurate than any of your measurements because it's not. So it doesn't matter that this has 2 sig figs and this one has 2. Your answer doesn't have 2 for that reason. It's that this one is only as precise, or the measurement here was only given to the ones place. But this one was measured to the tenths place. This is a more precise measurement. If you put this into your calculator, or you just did this by hand, the answer you would get, the raw answer, would be 22.8. But this is saying, yeah, I've got about 21. And this is saying, I've got about 1.8. Well, this answer is more precise than it should be. It's showing an answer that's more precise than what it actually is, because what if this was 21.1? What if it was 21.1? You don't know. Remember, the last significant figure that you record is an estimate. So it could actually be 21.1, which would change this whole answer to 22.9. Therefore, bottom line is, because this was only reported to the ones place, and even though this one's more precise, your answer can only be reported to the ones place, which means we need to round this up to 23. Your answer can only be reported to the ones place because this is your least precise measurement. That's the rule for adding and subtracting. We're going to practice that more in class, and you're going to have some time to practice it as well. Like I said, this is just kind of your first exposure. With adding and subtracting, your answer can't be more precise than your least precise measurements. You've got to look at the two things you're adding up. This one is less precise. It goes to the ones place. Your answer can only be given to the ones place, so some rounding needs to occur to get you there. Multiplication and division is much easier. Your answer, all you got to do is count sig figs. And your answer can't have any more total sig figs than the measurement with the fewest total. So this has 1 sig fig, this has 3 sig figs. Here's the answer from your calculator. You've got to round it to 1 sig fig. Remember, this 0 right here is a placeholder. This computation, this has 3. This one has 2. So my answer can only have 2. So I've got to round to 2 sig figs. This gets rounded down. Okay? So these are examples. We're going to do more in class. You're going to practice more. But these are the rules for multiplication and division. Right? And so that is